Okay. All right, so what is the inductive learning problem? How is it hard? And how can we solve it? Before we dive into the details of different algorithms and their different strategies and whatnot, let's look at this problem in the simplest form that we can. So here it is. I'm trying to learn a Boolean function, y, and it's a function of 4 Boolean inputs, x1, x2, x3, and x4. Okay? So this black box here is the Boolean function. Right? This is my goal, is to figure out what that function is. If I figured out what that function is, then tomorrow when a new set of x1 to x4 inputs comes along, I apply the Boolean function, and I get hopefully the same result as the real function. Okay? So this is the goal. Now what do I have? What I have is examples of the function. So here's a table with examples of my function. For example, my first example says that when x1 is 0, and x2 is 0, and x3 is 1, and x4 is 0, then y is 0. Okay? So I have 7 examples. And now, of course, my job is to induce what the value of the function for the other examples is. Okay? All right, over to you. How would you solve this problem? Let's see your suggestions. Maybe you'll come up with right here, right now, a new machine learning algorithm that no one has thought of. So, how would you solve this problem? Don't worry about it being a sophisticated solution. We're not going to look at sophisticated solutions to anything today. So, can you think of a simple way to solve this problem?
If-else statement.
Sure. If-else saying what?
Effect conditions on variable values.
Absolutely. So in fact, this is what we're going to be looking at, very shortly. But be a little bit more specific, right? So that's your language, right?
Mm-hmm.
But now, how would you, learn statements in that language?
How would I learn it automatically?
Yeah, exactly.
By building decisions.
No, okay. So here's the thing that's going to happen.
Looking at each example and.
Okay, so for example, right, I could say, right, if x1 is false and x2 is false and x1 is true and x0, x4 is false, then y is false, right? This is an if-then rule, right? And then I could have one of these if-then rules for each of these examples, right? These 7 rules get all these examples correct, right? Is this a good solution?
It might be good enough.
This is the whole problem, right? Is that this is not a good solution. Yeah.
Oh, I was going to say, wouldn't that kind of be overfitting the data if you keep all of the possible?
This would actually be maximally overfitting the data, or maybe, you could say that this would be the pessimal solution, like the opposite of optimal, right? The problem with this is that such a solution would only tell me what I already know, right? I don't need those rules for that. I have the examples to tell me that. Remember, the goal in learning is to learn a function that I can apply to new examples that I haven't seen before and get those right. What would happen with this solution on a new example? It wouldn't match any of them, right? I only have rules for the examples that are already there. This would be completely useless on new examples, yeah.
So what if we try to find the closest to the new item? Like, say, I already know 7 of these, and I get a new one, and I try to got some kind of a distance between what I already know and the new one.
Yeah, absolutely. This is the type of strategy that we can use. Okay, and now of course we can
We can just have a very large. Instead of saying like, okay, let me just do a bunch of random operations on these things, and whichever sort of operations actually fits all this data.
This is a good straw man actually. Why not just do something random, right? We could. The thing is that something random might not be that good, right? We want to do, in a way, what we're trying to do here is better than random, right? Chances are random will basically be as good as flipping a coin, meaning you'll classify half of your spams and non-spams and so forth, right?
We can be about half the time right.
No, but if being right half the time is good enough, then great. But you probably want to be right more than half the time. By the way, notice the following. Let's say you have a problem with 10 classes, each of which occurs 10% of the time, right? Being right half the time is a brilliant achievement, right? Because by flipping a coin, you're only right 10% of the time, right? So sometimes being right half the time is amazing. By the way, on the stock market, when you're trying to predict whether the stock is going up or down, being right half the time is not good enough, but being right 51% of the time is great. If you can reliably be right, because you can do many trades even per second, right? If you reliably write 51% of the time, you can make money. I'm oversimplifying a little bit, but if somebody says that they write 60% of the time, they're either lying or they're doing something wrong. In the stock market, 60% is out of reach. But 52%, hey, you could be on the way to great riches with 52%. Yeah.
I have a question here. So I was just looking at, for example, whenever x2 is 1, the output is 0.
Mm-hmm.
So while coming up with the model, do I need to have some intuition about what the relationships between them are? Because that may be a good relationship there.
Very good. So two things. First of all, this is where having any kind of knowledge about the problem can help, right? You bring that to bear and you start to see. The other one is that is exactly the kind of rule that we're going to be looking for. Aha, look, this too is predictive of the class being 0. It's not the whole answer, right? But we're not going to try to come up with the whole answer all at once. We're going to try to build it out of these pieces. Yeah.
I think it's just an approach to how you could do this. So you could have sort of like a weight or something assigned with each of the inputs. That could be like the probability, if this input is 1, the probability that the output y is 1, and then you somehow do some function of all of those, and if total is above some threshold, then you decide that y is 1.
Absolutely. See, you have just invented the naive Bayes classifier.
I've done
Which
a
is,
little bit of machine
oh, there you
learning
go.
before, so I
Oh,
kinda
so you didn't invent it. Darn. Okay, so naive Bayes is actually the foundation of span filtering, right? At least we don't know because they don't say for obvious reasons, right? But at least in the beginning, most span filters were naive Bayes, and I hear that these days most of them, still are naive Bayes with a lot of things on top of it. But yeah, this is the basic idea of the naive Bayes algorithm, right? For each of these x's, you compute, how good of a predictor of y it is, and then you combine them all, right? And we will see in more detail how to do this. Very simple, strategy, but actually very effective for a lot of things. Okay, so here's another way to look at this problem. Okay, or continue with the same way. That was what I had. But now let's look at we're never going to be able to do this again. That's why we're doing this in a small example here. I can actually look at the table of the whole function, right? Because it's only 4 Boolean inputs, right? So it doesn't have that many states. Okay. So now what I've done here is this table is the same one that I had on the previous slide, right? Those examples are still there, right? But in addition, I put in here all the other possible examples, okay? Except that the ones that are not in my training set, I have a question mark for. So for example, I've never observed 0, 0, 0, 0, so I have that with a question mark, okay? And the problem that we're trying to solve here is just this. I want to fill in those question marks. Okay? This is my problem. Right? What do I put where those question marks are? Right? And here's the first important thing to realize. It's a really basic thing, but it's very important. And even machine learning experts forget it some of the time. You can put any darn thing that you want in there, right? If you don't know anything about your problem, just the data doesn't get you there. Right? Machine learning is all about the data, but the first lesson is the data is not enough. You need something else. Right? With just the data, right? I know the values for the examples that I've seen, like this and this, but the others, like somebody said, do it randomly. Flip a coin for each one of them. Right? How do you know that that's going to be worse than anything else? Right? You have your super spiffy classifier technology. Why should that beat random guessing? The reason, and in practice, however, we do have super spiffy classifier technologies that does beat random guessing most of the time. But this is because it embodies something about the problem that actually turns out to be right for the problem. Okay? So the first lesson is that if you're in a state of complete ignorance, you can't do better than random guessing. You have to bring in something else. Right? Going back to the gardening analogy, right? Complete ignorance is like having all the nutrients but no seed. Well, you can have all the water and nitrogen and whatnot in the world that you want, no seed, no plant. Okay? So this is the first important thing to remember. The next thing is actually in this example, right? We're going to be able to do another thing that we're never going to be able to do again, which is this example is so small that this question that I asked, how you going to how will you come up with those say if then rules, right? In this case, actually, we can just try all of them, right? In general, we're never going to be able to do it because there's way too many, right? But this actually is a small enough case that we could actually try all rules, right? And there's another lesson here, which is in this case, right? There are 16 possible examples, right? 4 variables, 16 examples, right? I know 7 of them. There's only 9 that I don't know. So, when somebody said, well, the ones that you know, that's not a bad thing to have. In this case, it's not a bad thing to have. It's almost half. But in real examples, right, you've seen 1 billion email messages. How many possible email messages are there? 10 to the who knows what, right? Those billion are an infinitesimal. It would be like in this table only knowing one example, and that is still an overstatement, right? You will have seen 1% of 1% of 1% of the things that you could see. So just remembering what you know is really not going to get you off the ground. You'll be lucky actually if you ever see one of those exactly ever again, in many cases. Okay? So we need something better. And now notice the other interesting thing here, which is I have 4 variables, right? So I have 2 to the 4 states, right? So 4 variables, right? 2 to the 4 states, right? i.e. 16 states, right? So how many functions are there? How many possible functions are there of 16 Boolean inputs? Yeah, I know, but hey. People didn't answer. 2 to the 16. So generally, right, if you have, let's say, n dimensions, right, you have 2 to the n possible states, right? 1 for every combination. And then each of those states you could label with true or false, right? So you have 2 to that, right? Everybody got that? Right? This first 2 to the n is the number of states, and then the number of functions is 2 to the number of states, okay? Right? So look at this shocking thing that I just put here. This is 2 to the n. This is a doubly exponential function. Now you've all heard how, easy problems in computer science are polynomial and the hard ones are exponential, right? We in machine learning, we laugh at those people who say NP hard problems are hard, right? Ours are hard, those are ridiculous, right? We're not just dealing with an exponential, we're dealing with a double exponential, right? And when you're writing a program, if you have 4 inputs, you have to choose among 16 things. If you're trying to learn the function, you have to deal with, with 2 to the 4. It's an exponentially harder problem, right? So yes, there's a reason machine learning, hasn't been done from the early days of computer science, right? This is the problem that we're faced with. It's this double exponential, right? Even if your number of dimensions was small, this would be, really tough. Imagine now when your number of dimensions, instead of being 4, is like, say, 1,000, right? Now you have 2 to the 1,000, right? The total number of subatomic particles in the universe is an infinitesimal thing compared to that. Okay? So the bottom line is brute force is never going to work. Okay? And this is why generalization is important, right? Because the part that you've seen compared to what you're going to see tomorrow, to what you could see, is infinitesimal. Okay? Questions? These are simple things, but this is really what underlies, all the algorithms that we're going to be dealing with. This is the nature of the problem, right? This is also why it's, in many ways, very different from other things in computer science. Okay, so let's do the following, right? The space is too large, right? Let us just pick a language, right? Let's pick a type of rule, right? And then just, in this case, try them all, right? Let's see what happens. Again, this problem is small enough that we can try that. We're not going to try all possible Boolean functions, right? Even that is a lot, although in this case we could try it, but, right? To sort of like make this half realistic. Let's pick a restricted set of rules, or a restricted class of rules, and use those, okay? So, let's take your suggestion and just use, if-then rules, okay? Let us just use if-then rules of the form, if x this and x this and x this, then the class, okay? So, for example, this first rule says that if nothing, then the class, meaning that, every example is, you don't test anything, every example is true, right? Well, if you go look at, and now what we're going to do is this is what's called generate and test, right? We're going to create all possible rules of this form, and we're going to test everyone against the training set, right? And if there's a counterexample, we know it can't be the right rule, we throw it away, right? And we're going to do this until we find one rule that really does hold for every example in the data set, and then we can declare victory, right? Because, we don't know any better, right? So we do that, and then we try, for example, if x1 is true, then y is true, right? Meaning that y is true exactly when x1 is true, and false exactly when x1 is false. Is there a counterexample to that? Well, unfortunately, yes, there is. So this one fails. We try all of those, they fail. Now we try combinations of 2. Let's say, if x1 and x4, then y. Well, there's also a counterexample to this one. And then we try combinations of 3. All of those have counterexamples. Finally, we try all 4 of them. If x1 and x2 and x3 and x4, then y. There's also a counterexample to this. Okay? Moral of the story. I picked the wrong hypothesis class. Right? My hypothesis class was nice because it was small. On the other hand, it was so small that it didn't have the right answer. Okay? So this class doesn't work. All right? Well, let's try another. How about, here's a very popular and useful class. People use it a lot in medical diagnosis, for example. Actually, real human doctors use rules of this type. These are so-called M of N rules. M of N rules are, there's these 5 symptoms. If you have at least 3 of them, then you have pneumonia. Okay? Because, medical diagnosis isn't cut and dried, right? But what they do is a balance of evidence thing. Like, there's these things that kind of are indices of, say, pneumonia. Often you don't have all of them, but if you have at least 3 of them, then you probably do have it. Okay? And, the same thing can be used for lots of other problems. They also have the advantage that they're simple. And they're more powerful than just simple if-then rules that just test the values of specific variables. So let's try those M of N rules. So first of all, let's try the rule 1 out of x1. And this one, you can do only one, of course, because there's only one variable. Is there a counterexample? Yes, there is. 1 out of everything, there's a counterexample, right? So all these fail. Right? These all fail. Now let's try 1 out of these 2. Right? 1 out of x1, x2, meaning that y is true if either x1 is true or x2 is true or both. Okay? Again, these all fail. Right? There's counterexamples to all of them. Now let's try 2 of them, which is actually just a conjunction, right? But now, those we already saw, they all fail. Okay? But now let's try, for example, 1 of 3. Right? This is new. Y is true whenever one of these 3 is true. Okay? We try that, they all fail. Now let's try 2. This is getting more interesting. Like I have 3 variables, and if 2 of those 3 are true, then y is true. For example, if x1 and x2 are true, then y is true. x1 and x3, x2 and x3, but etc. Okay? Nothing else. Well, lo and behold, one of these actually succeeds. There is no counterexample to this in the data. And now we can try all the others. 3 out of 3, those fail. Right? Again, this is basically just the case that we had before. 1, 2, 3 out of these 4, those also fail. Okay, so at this point we can declare victory, right? We postulated that, this was an M of N rule. And there's only one that works, so that has to be the answer. Okay? So at this point we can declare victory and go home. But, maybe you should be a little suspicious, right? What we just did here in microcosm is actually what people do when they run machine learning algorithms on stuff, with many more subtleties that we'll see later. But at heart, this is what's going on. And what can we learn from this? Let's take a step back and look at what happened here, right? And then look at maybe what is not quite right and should be done differently or better, right? One way to look at what just happened is the following, is that in the beginning, I have complete ignorance, right? I don't know anything about my problem, okay? And then you give me a data set. Well, this is good to know, right? It's real information about the domain. But as we just saw, that real data set doesn't tell me anything about the examples different from the ones that I've seen, okay? So now I need one more thing. I need a piece of knowledge, right? But if I know, let's suppose that we really knew for real that the concept was an M of N rule, right? Then we could do the procedures that we just did and we would have gotten the right answer, right? So what happened with this is that each of these things removed some of our uncertainty. Having my data removes some of my uncertainty, but as we saw, it only usually removes a tiny fraction of the uncertainty because most of the examples remain unseen. And then I bring in my rule. I say, I assume, or I believe, or I know that this is an M of N rule. That removes a lot of uncertainty, right? It excludes all the possible C and Fs that concept could be, right? So that really reduces your information, your uncertainty a lot. It carries a lot of information, but not completely, because there's still a whole bunch of M of N rules and you don't know which one it is, right? But now, when you combine that rule with the data, on a good day, lo and behold, the right answer comes out, okay? So one way of looking at this is saying, what is learning? It's removing your uncertainty, right? The data itself is not enough. Your knowledge of the domain, let's say that you start with the knowledge that it's an M of N rule, right? That is not enough. But that plus the data on a good day will remove your uncertainty and you'll be left with the right concept. Okay? So this is one way to look at learning. Okay? Another way to look at it is the following. Well, gee, you really got lucky here, right? We had like this random Boolean data set. We didn't know most of the examples, and we postulated that this is an M of n rule. Great, right? What are the chances of that actually being the case, right? Well, notice this loaded word here. Learning requires guessing a good small hypothesis class. There is always guesswork involved in learning. Some people are not comfortable with that, right? They like the certainty of, I just build this deterministic program and then it does what it needs. To do machine learning, you have to be comfortable with the notion that it's guesswork, and you're not always going to be right. If in your application you always have to be right, it's unlikely that machine learning is a good solution. On the other hand, if your application is a search engine and people will keep using you even if half the stuff that you return is crap, this could be a good, problem for machine learning. Okay? This also means that your ability to make a good guess is very important, right? If I can guess a small class that actually contains the right answer, then the data will do the rest of the job, right? So one way to look at learning is, it's like the Clint Eastwood way, right? Like the Dirty Harry movies where he goes ahead and tells the guy, go ahead and make my day, right? He's been chasing this guy, throughout this warehouse. They've been shooting at each other, and finally the guy, is down on the floor, and then his gun is like a yard away, and he's trying to decide whether to lunge for the gun or not, right? And Clint Eastwood comes up to him and points his gun and says to him, well, do you feel lucky today or don't you, right? Because if he feels lucky, he can lunge for the gun, but maybe Clint Eastwood has run out of bullets, right? They haven't been counting how many bullets they have. So if he's lucky, maybe he can kill, Dirty Harry. On the other hand, if he does still have bullets, right, then he could get shot. So in the movie, right, this is being Hollywood, of course, the guy lunges for the gun and, Clint Eastwood still has a bullet and kills him, right? But the key thing is that, there's an element of gambling. It's informed gambling, right? It's not completely random, but you have to do that. That element is always present in machine learning. It would be nice if we had if you think about it, if you already knew the domain with certainty, well, then you don't need data, right? You're programmed. So when you're doing machine learning, it's almost always the case that you know things about the domain, right? You can suspect that maybe this is the case, maybe that is not. And then you have a lot of data. But at the end of the day, you need an element of luck. When we do the theory part of this class, we'll actually see that, just because you need luck doesn't mean you have to be completely in the dark. You can play the odds. You can be smart about how likely you are to be right and whatnot, right? For the moment, we'll pursue a more empirical approach to this, and the theory also has its limitations, but nevertheless, you're not completely taking a shot in the dark. However, the main lesson is you're going to have to make some guesses, and your ability to make those guesses well is going to be crucial to success. And this is part of why machine learning is fun, because machine learning is not just turning the crank on a large data set. It's using your understanding, your instincts, your intuitions, trying to find, an answer. This is a very important component.
Real quick question on that. The fact, I'm going to try to figure out how to phrase this so it makes sense. The fact that you need this kind of domain knowledge to guess a hypothesis class, does that mean that we should have some skepticism about whether machines can ever initiate machine learning? Like the human gardener will always have to be there at the end of the day?
This is a great question, right? So notice the following, that in machine learning projects in the world, the humans are there doing some of the work. The machines have not taken over yet, right? Ray Kurzweil says that that's going to happen soon, but most people don't believe it, right? Nevertheless, so we are bringing something to bear, right? But just think about the following for a second. Evolution that produced us is a learning process, right? Evolution started out knowing nothing, right? We were all amoebas, or we were all, bacteria or whatever, right? So somehow that learning process, actually produced us, right? Evolution is a big data problem, right? The big data is all these creatures exploring the world, right? So there has to be some regularity in the world that we can exploit, right? And what you want to do is hopefully encode this into your algorithm so that you don't have to put them there yourself, okay? The other side of this, right, is that, well, you could be wrong, right? You could be wrong even if things seem to work out. Look at this here. right? Hey, I postulated that it was an M of n concept and I found only one that fit. Does it mean I should go home happy? Not really, right? Because if you think about it, there's other things that would work here, right? So for example, the rule, you can check this yourself, at home. The rule x1 and not x2 implies y also works. So which one is it? If this is the true one and we guess the M of n one, we'll get all our stuff wrong, right? So we could be wrong. And you can never be sure that you weren't wrong. In some cases, you can have high confidence that you were right, but you can never be sure that you were wrong, that you were right. Okay? You could always have been wrong, and you have to be comfortable with that. Okay? However, notice the following. There's a trade-off in the size of the hypothesis class. The smaller I make the hypothesis class, right, the more information is encoded in that, the lower the burden the data has to bear, the easier the problem becomes. On the other hand, the more things I've thrown out, the less likely that the right hypothesis actually will be in that class. So in a way, you want to make the hypothesis very small to make the learning easy. On the other hand, you want to make it very large to make sure that the right answer is in there. And there is an inevitable tension between these two things. Okay? In practice, how do people deal with this tension? By trying successively larger sets of hypotheses. I start out trying something very small. If that works, looking pretty good. If that doesn't work, then I try a larger set and a larger one. Just like we did with the if-then rules and then the M of n concepts. Okay? The larger the set that I try, the less I'm going to be sure that I found the right answer. Right? Because I need less luck to have found the right answer. Okay? Nevertheless, it's very good to have that ability to try successively larger hypothesis sets. And this is exactly what many algorithms do. In particular, decision tree learners work that way. As we will see next week, they start out trying very small hypotheses, very small trees. If that doesn't fit the data well, then they try larger trees and larger until they either fit the data well or they decide to stop earlier to avoid overfitting. Okay. Questions about this? Okay. So, out of these two observations come two strategies for doing machine learning. And we're going to see them in action in the coming weeks in a bunch of different ways. One of them is, since it's so important to express and use prior knowledge to make our learning easy, one of the things that we should have is languages in which it's easy to express the kind of prior knowledge that we have. Right? And in fact, for example, something that is popular in some quarters is, I'm going to allow rules with only a particular syntax on the antecedents. I'm not going to allow any antecedents. I'm going to allow antecedents that obey these rules. For example, I might know that certain variables cannot appear negated because they're positive indicators of the class. This is a common thing, right? These are useful restrictions to have. We want to have languages in which it's easy to say those things. And in fact, one of the main criteria for choosing representation is which representation makes it easy to encode the knowledge that you have. I've never seen this in the textbooks, unfortunately, but this is actually crucial. Part of the choice of, should I use a set of rules or should I use instance-based learning is the stuff that you know. Is it easy to write it down as a set of rules, or is it easy to say what makes two people similar? Right? If writing down rules for diagnosis, like if you have this temperature and this X-ray, then you have TB, right? Then use rule sets, right? If it's easier to say well, I know how to compare people, right? I compute the Hamming distance between them, and that's what makes them similar. This, of course, is a naive example, but in that case, maybe you want to use something like instance-based learning, okay? So the choice of language should be very much influenced by what kind of knowledge you have and what language makes that knowledge easy to apply, right? You shouldn't have, like many people, this one language that you always want to use. You just use decision trees. Well, no. Sometimes they'll be the wrong thing, okay? So this is one notion. The other one that we just touched on is what you want to have, right, is flexible hypothesis spaces. We're going to look at some simple machine learning algorithms like naive-Bayes, for example. They have a fixed hypothesis space. Those are nice and simple. They're often very efficient. When they work, life is good. But a lot of the time, maybe even most of the time, that is not how you get the best results. And then you want algorithms like, say, decision tree learners that are flexible in the hypothesis space that they consider. In particular, they can start out with a small hypothesis space and then only extend it as needed. Okay? With either of these strategies, at the end of the day, you still need to develop algorithms that will find a hypothesis in that space using that language that fits the data. Okay?